today we are going to have Dan, and Dan has received a PhD from Michigan, and he was at Texas A&M before joining Northwestern in 2003. And Dan has been supported by numerous industry and government agencies, including NSF Career Award. And he's a fellow of the American Statistical Association. And Dan has also received the IIE Transactions Best Paper Award, the Technometrics Wilcoxon Prize, and the Journal of Quality Technology Lloyd S. Nelson Award. Dan also has served as editor-in-chief for Technometrics, editor-in-chief for the Journal of Quality Technology, chair of the Quality Statistics and Reliability section of Informs, and also the director of the Manufacturing and Design Engineering program at Northwestern. So Dan works on the problems at the interface of engineering modeling, statistical analysis, and predictive analysis. And today he will tell us in this seminar about the new tools he has recently developed for understanding black box supervised learning models. So please join me welcoming Dan.
Thanks, Chung-Han, and thank you for inviting me. And thanks to everybody for coming. Let's see, let me share my screen. So I normally, when I give department seminars, other places, I usually stick to one topic and go into a little more detail. And I thought I'd just cover a couple different topics, related topics, but not related in the sense that both the topics I'm going to talk about are, the setting is you fit a supervised learning model, some predictive model for predicting a response given the set of predictors, maybe a neural network or a boosted tree or random forest or whatever your favorite model is. And you want to understand what's in the model, how the different predictor variables affect the response, because these models are all black box and not as transparent as a linear regression model. And then other diagnostics. If the predictive relationship is unstable over your training data, if it drifts, that's something called concept drift in the machine learning community. You know, how do you detect that and diagnose it? So first topic is the first thing I mentioned, where I've got a slide with more details here. So here's the setting. And let me get my pen working. Oops. Okay, so setting is you fit your supervised learning model. I'm calling it f of x. I probably should put a hat over f because it's something you estimate from a set of training data. And you can really think of it as just y hat of x, the predicted response. I don't know why PowerPoint added that long straight line, but it did. So you've already fit your model and tuned it. You know, choose all the regular tuning parameters that you need to tune, and you think it's a decent model. And then now you just want to understand it, understand what's inside the model. And your x, that's a vector of predictor variables. So little d is the number of different inputs or predictor variables. Y is the response variable. N is the number of training observations to which you fit the model. If in a regression setting, you can think of f of x just as being the expected value of the response as a function of your predictors. Or for a classification problem, you can think of f of x as being the probability y falls into a particular response class as a function of your predictor variables. So if it's linear or logistic regression, the simplest and oldest methods, then you don't need any of this because each predictor has its own coefficient, regression coefficient. And if you want to know how the predictor affects the response, you just look at the coefficient. Maybe look at its p-value, statistical significance. And if the coefficient is positive, that means when you increase it, it increases the response and so on. But all these other, fancy machine learning models, supervised learning models people use, simple trees are pretty easy to interpret if you got maybe 20 or fewer leaf nodes, but anything bigger than that, it's hard to interpret. Random forests, neural networks, boosted trees, support vector regression or classifiers, nearest neighbors, kernel methods, you name the method, and it's basically black box. You can't look at the fitted coefficients to a neural network or anything inside of a boosted tree and get insight on how the different predictor variables affect the response. So this is the goal, and what the scope of this work is. It's a follow-up. It's basically a graphical procedure for taking a fitted model and plotting things like the predicted response versus individual predictors, in which case you have to kind of average out, in some sense, to be defined later, the effect of the other predictors. Well, that would be sort of the main effect of individual predictors. But then if you have two or more predictors that interact with each other, that doesn't show you the whole picture. So it's also doing things like plotting interaction plots that show you the combined effects of pairs of predictors. And I got an example. Maybe I'll just start with an example just to and show you the result, sort of, to give you an idea of what a more concrete idea of what the purpose of this is. This was a publicly available data set, bike sharing data in Washington, D.C. area. The response, each row of data, there was like 18,000, 17,000 regression rows. Each row was 1 hour. And the response variable Y was the number of bike rentals in that hour. And then the predictors, I think there were quite a few in the original data set, but we looked at 11, 8 numerical predictors, the month of the year, because the bike rentals numbers depend on the month, hour of day, day of the week, weather situation. This was coded as numerical on a scale of 1 to 4. Larger is worse weather. The temperature, something called A-temp, which is, they refer to it as feeling temperature, which I think in the summer is like the heat index that takes into account humidity. And then in the winter, it might be the wind chill that takes into account wind speed, and then humidity and wind speed too. So there's lots of correlation between the predictors. 3 categorical predictors, the year, this was just a 2-year period. And then whether or not it was a holiday, because the rental patterns depend on holiday or not. And then whether it was a working day. Either weekend or holiday is not a working day, or weekday is a working day. So that was the data. Then we fit a neural network to it. Neural network fit pretty well. We tuned it with cross-validation. We used the R package, and that used cross-validation to choose all the tuning parameters, the regularization parameter, and the number of hidden layer nodes. And then it was a pretty good model in the sense that the cross-validation R squared was 90%. So good predictability for the data. So next,
can I ask you a question?
Oh yeah, please.
Yeah. So actually the month of the year and the hour of the day and day of the week, and those are numerically coded, but they are really categorical variables, right? You don't want to think that month 1, 2, 3, 4 have any numerical.
Yeah, I guess it's in a situation like that where you got a categorical variable, predictor variable with lots of categories. I mean, this is sort of an ordinal categorical, right? Month is ordered. January is closer to February than it is to July. And so if it's ordered categorical, with a linear regression model, you got to be careful coding it as numerical because it's linear. You assume a linear relationship. But with nonlinear models, I think if it's ordinal categorical, I think you always want to convert to numbers, because if there's a nonlinear, if your numerical coding is off of what it should be for a linear model, the nonlinear methods can kind of catch that. And so I treated all these. I mean, you're right, it is really categorical, but
yeah, I mean, the number should not be, the numerical coding should not be interpreted literally as numbers.
Well, let's think of it a different way in terms of, what I'm going to show you in a minute. Maybe I show you it now. So here's the method that we developed. I call it accumulated local effects plots. And this is joint work with my student, Jingyu Zhu. It creates plots like these. The vertical axis, you can view as, I haven't defined it yet. I'll define it shortly, but you can think of it as the predicted response from the neural network model versus each of the individual predictors. So here's with month coded, January is 1, February is 2, and so on. here's how the number of bike rentals, the predicted number of bike rentals change as a function of month. Right? January is lowest, February is a little higher, March, April, May, kind of peaks over in September. And then August, September, and then goes down. You know, if you just keep it as categories, this method does apply to categorical predictors too. If you don't, you know, if you didn't order the categories, I mean, there is some smooth behavior, right? March and April should be pretty close. January and September should be further apart. Right? So I think it just makes sense to, you know, to code it as numerical, or even just, I guess you get sort of the same result if you just ordered the categories here. But why? When you fit the neural network, you might get different results. Does that make sense, Ajit?
All right. Yeah. Okay.
And then, so here's for the predictors, what the results produced. And again, the point of this is just to help you understand how the different predictor variables appear in the model and affect the predicted response. And you can see with month, what we just said, it's sort of lowest in January and then slowly ramps up over the course of the year and peaks and then goes down. Hour of day, that makes sense, right? This is the 8, 9 a.m. rush hour. You get a peak up here, and then it drops down in midday, and then you get a peak in the evening rush hour, and then it drops down. Weather situation, 4 is worse weather, you know, rain, snow. 1 is better weather, so that goes down monotonically with weather situation. Wind speed, the bike rentals go down monotonically with wind speed. And these are what we call main effect plots that just show you the in a sense to be defined shortly, the averaged effect, average predicted response as a function of the one variable averaged somehow across the other variables. But you're missing if there's an interaction. If a pair of predictors interact strongly, you miss that with the main effect plots. So the method that we developed also produces interaction plots. Don't look at this one. This plot over here is the second order interaction plot showing the combined effect of 2 predictors, hour of day and weather situation, right? And you can see those rush hour peaks when we did the main effect plot of hour of day. If it's good weather down here, draw a line across here, the contours and the numbers here, it's a heat map and a contour plot of, you can think of it as the predicted response as a function of these 2 predictors. You know, again, averaged in the sense to be defined shortly over the other predictors. So if you look at the predicted response along this line, the rush hour peaks here and here are much more pronounced, of course, than they are if you got bad weather up here. Right? You still have peaks, but it's a lot smaller. So that's sort of I still haven't told you what these are exactly, that's coming up shortly, but that's sort of the scope. The objective is you fit a supervised learning model and you just want to understand it. You want to understand how all the different variables affect the predicted response and appear in the model. You know, why do you care? Why do you want to do this? If, you know, generally speaking, you fit regression classification models like this for 1 or 2 reasons. Either explanatory purposes, in which case it's obvious why you want to know what the effects of the predictors are, like, you know, medical risk factor studies where you're trying to understand what possible risk factors like smoking and eating habits and things like that, and ethnicity, how they affect risk of heart disease. But if you're fitting the model just for purely predictive purposes, it's still a good idea to understand what's in the model. And this is getting more common now with the explainable machine learning and interpretable machine learning. This sort of appeared in the last few years. I mean, that's sort of the goal, you know, beware using a model that you fit until you can kind of explain it, because it might not be reliable. Sometimes you have to do this. I had a project 10 years ago or so with credit risk and Discover credit card company, trying to predict somebody applies for a credit card, you want to predict the risk of defaulting on the credit card. And in situations like that, they're highly regulated. You can't use the model unless you can sit down with federal regulators and convince them that you don't have anything like race that appears in the model, or, you know, any of the things that you can't penalize people for, age, you can't give somebody a worse credit score because they're older. So you know, in those cases, you have to be able to explain the model or you can't use it. And then I like to think of it as, you know, if you go back to, look at this. Let's say this axis was some medical risk study and you fit some classification model to it, and this was the risk probability of heart disease. And this variable, let's say, was the age of a person. If you fit your neural network and you thought it was a good model, you thought you tuned it properly, and then you created one of these plots and it showed you this, that the risk of heart disease goes down with age, you'd want to know. It means, you know, one of two things: either you discovered something really surprising and new, or what's more likely, you got some bad data, or if you fit the model wrong, or there's something wrong with your data. But either way, you want to know about it. It's a challenging problem. If all of your predictor variables were independent, then it would be actually a fairly easy problem. And you could use, you know, old existing techniques. The problem is when you've got dependencies, correlations between the predictors, you know, all the existing methods really have serious problems in that case. So this is what sort of motivated the work. And some existing methods, really the main existing method was what's called partial dependence plots. The other methods aren't, there's something called functional ANOVA, which kind of is intended to take some black box function and show you how the different variables impact the response with interactions and main effects. And people never use these for machine learning models. Just there's computational nightmare. And then it's got also serious, most of the functional ANOVA was developed for independent variables. Like if you got some computer simulation model and you can actually control the variables, right? With machine learning models that you fit, you always fit it to observational data where you can't control the correlations, and in almost always you get strong correlations between at least some of the predictors. Something called coplots and ice plots, they're not quite the same either. Those really are fixing the value. X\J is notation for your set of predictors excluding the jth one. So if you want to understand the effect of xj, ice plots basically just fix values of the other predictors and then just plot the predicted response as a function of the one predictor. That can get kind of messy because you're plotting a series of plots on one plot. So the main, the main method that does, tries to do what our approach is doing is called partial dependence plots. So what are they? Let me just give a little bit of background. I'm also going to talk about marginal plots too. People never really use it for these reasons, for the reason I'll talk about in a moment, but at least it sets up a problem that partial dependence plots get around. Marginal plot, let me illustrate with just a simple example where, let's say you've just got two predictors. Little d is the number of predictor variables. So two predictors. Here's a scatter plot of your training data, x1 versus x2 for your training sample. The predictors are highly correlated here. What a marginal plot does, something is a function that I called f1 of subscript m as a function of x1. The subscript 1 means it's for x1, the first variable. So what this plot is you would discretize the x1 axis into, my pen is getting really slow here. So you discretize the x1 axis maybe into 50 points or something like that. And then for each value of x1, the marginal plot value is the expected value. You plug in that fixed value of x1. You take the x2 as the random variable, and you take the expected value of the predicted response using the conditional distribution of x2 given x1. And that's the theoretical definition. How you would compute that in practice given a set of data. You'd basically just bin up you discretize the x1 axis into bins. And then at a particular value of x1, you look at all the, let's say this value right here. You look at all the training observations that fell in the little bins surrounding that value. and you just literally take the average predicted response within that bin. And you can see why nobody uses that for these purposes. It's because if you want to predict or if you want to compute the mplot value for another value of x1 over here, and you'd calculate the average predicted response in this bin, well, both x1 and x2 changed because they're correlated. So if the average predicted response is higher over in this bin, you don't know if it's because x1 changed or x2 is higher. It's so basically mPlots would conflate the effects of two predictors, and so you never use them for that reason. Partial dependence plots are an old method. I think Jerry Friedman was the first to come up with that, and it was all in the context of his boosted trees, but you can use it for any supervised learning model. How a partial dependence plot gets around conflating the effects of predictors is, if you want to calculate the partial dependence plot value for, let's say, this value of x1, you still use the expected value of the response, but you no longer use the conditional. mplot uses the conditional distribution of x2 given x1. Partial dependence plot, when you take the expectation, uses the unconditional distribution. Right? So you would basically be, my pen's really slow here. You would basically be plugging into your neural network model or whatever model you fit, you would be plugging in x1, x2 combinations everywhere along this line. And then averaging the predicted response. And you can, if you think about it for a minute, you can probably see what the problem with that is. You don't have any, your training data is only over in this region. You don't have any training data at all up in this region or over here. So the model wouldn't be reliable. When you plug in x1, x2 values in that region, you might get nonsense predictions because you had no training data there. So that's the main problem with partial dependence plots, is that it has to extrapolate outside the envelope of the data, and you can get kind of bad, unreliable results because of that. And then partial dependence plots are also really computationally expensive. What we developed, AL plots, are a lot faster too. So this is basically the main idea behind this AL plot approach. Right? Remember, what does a marginal plot do? You're using the conditional when you take this, when you average the predicted response, you're using its conditional distribution, conditioned on that value of x1. Right? So that means you only have to plug in values within the, within the distribution of the data. So you don't have to extrapolate with mPlots, but then they conflate the effects of two predictors. So the main idea behind AL plots is, don't average the predicted response itself, average the local effect of the predicted response. Local effect just being the derivative. So you take the partial derivative of the predicted response with respect to the variable of interest. So that would be, at this point, if you want to calculate the AL plot value at x1 equals 0.3, for each of these sort of training observations that appeared here and over its distribution, you'd calculate the local effect of x1, the derivative, and then you'd average the derivative in this region over all values of x2 that occurred in that region. Okay, and that would just be the average local effect. If you want to get the value of that to plot, you have to accumulate or integrate that local effect from some lowest level, usually the smallest observation you had. You just accumulate or integrate that partial derivative up to the point that you're going to plot at, and then that's what you'd plot. And then you'd repeat. You again, I didn't mention this, but I should have. You'd start by discretizing the x1 axis into 50 or 100 points. And then you would compute an AL plot value at each one of those points. And at each one, it would be the integral from some lower limit up to that point. So you're taking the average local effect and then accumulating it, and hence the name, accumulated local effects plots. You know, that's the gist of the idea. Any questions at this point? Okay, so I've just illustrated it for the case where you got two predictors. In general, when you get D predictors, idea is the same. The AL plot that you would compute and plot for the jth predictor, you discretize the XJ axis, this range up into 50 or 100 points. And then at each point, you take the expected value of the derivative, the local effect with respect to XJ. And then the expectation is with respect to all of the other predictors using their conditional distribution, given that value of XJ. So the conditional distribution is what avoids extrapolating beyond the data range. So you got the average local effect, and then you integrate it. And then you might wonder, well, what do you do if you're fitting a model like a tree or a tree-based method, like a boosted tree or random forest? It's non-differentiable at points because trees have jumps in them. There's no problem. We got another, I didn't put it in the notes here because it's a lot more messy mathematically, but there's a definition that works perfectly fine for discontinuous predicted models that predict the response discontinuously. Basically just replaces the derivative with finite differences, and then the integral with summation, and then takes the limit as the differences go to 0, and it all works out fine even for discontinuous predictors. And then, the nice thing is, this is just sort of the theoretical definition. In practice, given a set of data, training data that you fit the model to, you can think of it as the estimator of this function. That works the same way regardless of whether you're using the, the continuous or the definition for non-differentiable. You basically just replace the derivative with finite differences across the bins when you bin up the XJ range. And you replace the expectation with a sample average within the bins. And then you replace the integral with a summation. Yeah, and that's what this slide illustrates.
What is the constant you're subtracting?
Oh yeah, sorry. The constant, I subtracted, I don't know if it shows over here. Probably, yeah, I added the constant back in already, but so this would be the non-centered version of the main effects. Subtracting the constant is, the centered version. And then the constant I subtract on the main effects, the constant is just the average. You take this function that you computed.
Okay.
Right, you take this function that you computed as a function of xj, and then you plug in the training values of xj, and just take the average function value and subtract that. And so that's how I defined all these, main effects. I just defined it convention-wise as being centered by subtracting out a constant. And then same thing when I'm going to define interaction effect in a minute. That's the same thing. That's centered in the sense that as you subtract out the main effect functions from that function and the average. Let's see. Yeah. So just ignore all the notation on this page. I think I could just illustrate with a plot here. And so this shows how you would compute the AL function for the first predictor x1. So here we got 30 training observations, just a little small toy data set to illustrate. This is a plot of x1 versus x2, not the response. Shows the correlation in the predictors. 30 training observations, take the x1 range for your training data and broke it up into 5 bins. Capital K is the number of bins. In practice, you have a bigger data set and you'd use maybe 50 or 100 bins. But this is just to illustrate. So here we had 5 training observations that fell into this bin over here. You would, for each of these x2 values in that bin, you would compute the local effect of x1, which would be just the difference in the predicted response from the left edge to the right edge of the bin. So you do that for all 5 of these points. And then you'd average those 5 local effects, right? And that would be your average local effect in that bin. And then to get the actual AL plot value that you plot at this value of x1, you would just start at the lowest value and you would sum up the average local effect for all the bins up to that point. So the computation of AL plots is pretty fast too. It's for reasons mention later, it's orders of magnitude faster than partial dependence plots. Because partial dependence plot actually has to, for each bin in the partial dependence plot, you don't just plug in the observations in that bin into your predictive model. You got to plug in all n x\j values into the neural network for every, every partial dependence plot point you want to plot at. You got to plug in basically n. You got to plug into your predictive model n times. Whereas AL plots, cumulatively across, to compute the AL plot for every value, you only have to plug in n times total. Yeah, so if there's any questions, if anything's unclear, then feel free to ask at this point. That was the main effect definition. For the, if two variables interact, let's say xj and xl, if they have an interaction effect in your model, which is really, really common, you're missing that. If you just do the main effect plots, you miss it. So the second order interaction AL effect for two predictors is same idea as the main effect, but you just replace the first derivative by the second derivative with respect to the pair of predictors. So that's like the second order local effect of xj and xl. And then you take the expected value of that with respect to all your other predictors, excluding xj and xl, using the conditional distribution, given those two predictors. And that's your averaged or expected main effect, second order effect. And then you double integrate it from some lower limit of xj and xl. And then the estimator is the same logic. You'd replace the second order partial derivative, you would replace with the second order finite difference. The expectation you'd replace by a sample average, and the double integral you'd replace by a double summation, which is what's illustrated here. So here's two predictors, and again, ignore all the notation on the right. You got two predictors now, xj and xl. You would bin both of them up into bins, and then you take the Cartesian product, and that'd give you a grid. If you want to compute the second order AL interaction effect, let's say at this point right here, we had two training observations that fell into that bin out of our n training observations. So for x\j values for these 2 points, for each of them, you would plug in the 4 corner points for xj and xl into your predictive model, along with the x\j values that actually occurred. And then you'd take just the second order finite difference over the 4 corners. And you get one of those second order differences for each training observation that fell into this bin, this cell. Then you'd average that across all the observations. And that's your averaged, that's your estimate of the averaged second order effect. And then to get the AL plot value back that you plot at this point, you just double sum the second order, average second order differences for all points up to, from the lower right up to this cell. Okay, so that's, oh yeah, and then back, I subtract out something from that to get the second order effect. And what I subtract out is once you compute this function here, that function itself, you can calculate its main effect for the 2 predictors. So I subtract out the main effect functions of this function, subtract them out, and then subtract out from that, I subtract out the average. So basically that just zeros. And that's, I don't know if you noticed it back when I showed the interaction plot. This left plot that I said don't look at, that's actually the zeroed or the centered second order interaction. So it doesn't have any main effects in there. And I like to plot both. I like to plot the zeroed one because then if you look at the contour values, the numbers, it's easier to gauge just how big the interaction effect is just by looking at the numbers. To actually understand the joint effect of the 2 predictors, though, I like to plot this plot here, which is, I guess I haven't mentioned that. It's not, it's not that original function before you center it. What it is the centered value And then I added in the original main effects for the two predictors. And then I added in the constant. And so you're just adding together to look at the second order combined effect. You take the centered second order interaction plus the centered main effects plus the overall constant, which is basically just the average response over your training data. And the reason I do that, there's like an ANOVA type decomposition. If you're familiar with the Sobel decomposition of a function into its main effect, the sum of its main effects and its second order effects and its third order effects and fourth order effects, there's an analogous AOPLOT decomposition that says, any function can be represented as the sum of all of the centered main effects plus all of the centered second order interaction effects plus all of the centered third order interactions and so on and so forth. Well, let me go back to this example. I already showed you some, I showed you some of the main effects, and they all kind of make sense and are revealing, right? It shows you how the bike rentals depend strongly on the hour a day. You get the rush hour peaks. Shows you how the effect of the weather situation, as the weather worsens, the bike rentals decrease by this amount. And here's the effective month. And then I showed you one of the main effect plots that are interaction plots that make sense. There's a couple more things that, those were all kind of obvious. It didn't really show us anything you wouldn't already have guessed, which is good in this case. But there's a couple of things that weren't as obvious. Where am I? Oh, here we go. One thing that wasn't obvious, and this, I guess this is not so much a non-obvious one, but this is just showing how partial dependence plots can break down sometimes. So here's the effect, the main effect of feeling temperature, right? Like heat index or wind chill in the winter. So the main effect of heat index, the left plot is the AL main effect. The right plot's the partial dependence main effect. And look at for the AL plot, what does it say? It says the main effect is the feeling temperature increases, the number of bike rentals increases up to some peak. And this peak occurs, it's 24 degrees Celsius, which I think is like 74 degrees Fahrenheit, something like that. And this is feeling temperature too. So I guess, with a little bit of humidity, the actual temperature might be lower at the peak, might be lower than 74 degrees. But, to me, that seems like kind of an optimal biking temperature, right? And with a, heat index of 74 degrees. And once the feeling temperature gets higher than 74 degrees, bike rentals start to go down. For example, if you're up at 40 degrees, which is heat index of over 100, the bike rentals go down substantially, which makes sense. Here I wouldn't place too much stock in this because I think there was only, there was probably no training data up here, maybe just 1 point or something up in this region. But at least up to 40 degrees heat index centigrade, you got enough data where I think this is reliable. Partial dependence plot didn't show that. And keep in mind, both the AL plot and partial dependence plot were computed for the exact same fitted neural network. It's just the partial dependence plot thought as the feeling temperature increased, the rentals continuously went up. So there's a difference here. This shows, basically the point of this slide is to show that there can be a substantial difference. I think the AL plot's more reliable for two reasons. Number one, it makes more sense intuitively that there's an optimum biking temperature. And if you're either too hot or too cold, people don't want to bike. And then number two, we already know the partial dependence plot has to extrapolate. And since we included, lots of highly correlated predictors, the actual temperature, the feeling temperature, the humidity, the wind speed, they were all included. There's lots of correlation. I think just the extrapolation that the partial dependence plot had to do was not reliable. Another difference between AL plots and partial dependence plot, the AL plots are orders of magnitude faster. I mentioned why earlier. Basically, AL plot just has to plug in to the model. Well, I guess if you're doing the AL main effect, you have to plug into your predictive model 2 n times, or n's the number of training data. Partial dependence plot, if you discretize the x-axis up into 100 points, you got to plug into your predictive model 100 times n times. And then it's even worse if you're trying to compute an interaction plot. If you discretize the x1 and the x2 axis up into 50 points each, that's 2,500 different points. Partial dependence plot has to plug in 2,500 times n different times into your machine learning model. So really, really slow. And for this example, it took less than a second for each AL plot. And it doesn't matter if it's main effect or interaction, they both have about the same computational expense. Partial dependence plots took 25 seconds for each main effect and 8 minutes for each interaction plot. Well, there was another thing that was kind of interesting in this example that the AL plots revealed. They actually also have kind of a built-in, or a related at least, variable importance measure. And if you've ever seen variable importance, in global sensitivity analysis and ANOVA, related to ANOVA decompositions, different variables in some black box function have main effect importance. That's sort of a measure of their overall importance of their main effect. And they've got interaction, total importance measure, which is intended to measure how important a variable is when you consider its interactions with other variables. AL plots have a really, really kind of trivial built-in main effect. We looked at 2 different importance measures, 2 different classes. One was derivative-based, which I don't really like. In general, I don't think derivative-based measures are good for these type of models. So ignore this. So we've got sort of variance-based measures, and we've got a main effect variance and then a total effect variance-based measure. The main effect is a no-brainer. It's just the variable importance measure, let's say for xj, that's just the sample variance. If you take the main effect, f, I'll put a hat over that, fj hat AL, sorry, that should be an I equals 1, 2, to n. So after you compute the main effect function of xj, you just plug in the n training values of your jth predictor, and you just look at the sample variance of this, and that's the main effect VIM. The total effect VIM was not so straightforward. We have a definition. I don't even, let's see how much time. Oh, I'm getting short on time, so I don't think it's probably not worth the mathematical overhead to try to define that, but just at this point, just take it as some measure of the total importance of the jth predictor. So we computed them for each predictor, and here's how the 11 predictors in our model are ordered in terms of the largest importance to the lowest importance. If you look at the total effect, x3, the hour of day, and these are sort of variance-based measures, so I probably should have taken the square root of it and plotted that. Then it'd be in units that correspond more to the response. And this first one won't look like it dominates so much, and the second one would be closer. But the most important variable was hour of day. Second most important variable in terms of total effect was the workday. So if you saw that, if this was your data set, the next question you would ask, well, how does hour of day and workday affect the bike rentals? We already kind of know how hour a day affects it because we looked at the main effect plot. Workday, though, if you look at the main effect importance of x6, workday, it was the smallest. So workday's got no main effect, meaning on average, you neither have more rentals nor fewer rentals on a workday versus not a working day. And yet it's important. So that tells you one thing. It tells you it has to interact with at least one other predictor. So the next thing you do is probably start picking out other predictors that are important and looking at their interaction plots between workday and then here's the interaction plot between workday and hour and the interaction plot between workday and temperature. The one between workday and hour is kind of interesting, and actually after you see it, kind of obvious. This was just me getting sloppy when I coded and made the plots. Jingyu has improved on this. There's really only two values of work. It's binary. So it's either not a working day. So value of 1 is not a working day. Value of 2 is a working day. So if you just kind of look at the partial dependence plot value in this region. So those two curves are what's sort of important here. If it is a working day, then it's that rush hour phenomenon, right? Around 9 a.m., you got a rush hour peak, or 8:39. 5 or 6, you got a evening rush hour peak. In the middle of the day, it goes down, but it goes down a lot more than it did when you just looked at the main effect. It goes down substantially more in midday, the rentals. Why? Because the main effect sort of combines these two curves. Whereas if you look at, if it's not a working day, you got no rush hour peaks. It's just in the morning, or wee hours of the morning, you get very few rentals. And then just the number of rentals slowly increase up till midday where the rentals peak. And then it slowly goes down as the day increases. So a strong interaction. And if you just looked at the main effect of working day, you'd miss that. Working day also, or even hour of day, if you look at the main effect, you'd miss it.
So what are those contour lines between 1 and 2? Are they kind of interpolated somehow, or what is the interpretation?
Good question. I gave, if you want to do a heat map in R, you give it a matrix. You have to do it on a grid. So you'd give it a vector of X6 values and a vector of X3 values, and then a matrix of whatever you're plotting. I don't know how it interpolates that matrix, but
yeah, because only the values at 1 and 2 are meaningful. So.
Oh yeah, and like I said, this is me getting lazy when I first coded this and did the plot. Jingyu has since done a better job, and I think maybe only plots it on, wouldn't show all this stuff in between, which is not. Oh, interpolation here. You meant interpolation with workday. Yeah, right. Just ignore the interpolation workday because I shouldn't have plotted it. Me being lazy. And then same thing over here. The interaction between workday and temperature is kind of interesting. If it is, it's pretty much the same shape. If you plot the combined effect of workday and temperature along these two lines, the trend's the same for both, either working day or not a working day. There's kind of an optimum temperature for biking. And if you're either above the optimum temperature or below the optimum temperature, the rentals go down. But it goes down differently. If it is not a working, just by looking at the shape of the contours, if it's not a working day, when you deviate from that optimal temperature, the rentals go down more quickly than if it is a working day, which I guess kind of makes sense, right? If it's a, if it's a work day, a lot of the bike rentals are people who bike to work. If that's your routine, you get in the habit of biking to work. Then if the weather's not perfect, you're still inclined to keep your routine. Whereas if it's a holiday or a weekend and you're, vacation or biking around Washington, D.C., if the heat index is 100 or 35, the wind chill, you're a lot less likely to bike. Well, I had some other stuff I was going to show. I guess I'm getting short on time, and I just wanted to mention one other topic. Before I was going to spend the last few minutes just briefly overviewing one other topic. Before I leave, any other comments on this or questions?
So I have two general questions, but I think I'll wait till the end.
Okay. And we've got the software, the AL plot is an R package, capital ALE, capital PLOT, one word, it's an R. There's been, GNU's going to do a Python package, but some other people beat us to it. There's a couple other groups that had, based on that did basically a Python implementation of AL plots, if you want to use it in Python. Well, just really briefly, another topic that's sort of related, but different. This is, if you've heard of concept drift, this is an approach for concept drift monitoring. This is work with Koongang and my former student, I guess Koongang's former student now also, but my former student Andui. This concept drift means you're fitting a supervised learning model to a set of training data. The predictive relationship, if you want to think of it statistically, you can view a supervised learning model as representing the conditional distribution of your response Y as a function of your predictors for either regression or classification. If it's classification, the predictive distribution conditional would be just a discrete categorical distribution. If it's regression, it'd be continuous. You fit it to a set of training data and observations that's usually collected over time or over space. And then you use the model to predict new data going forward. But what if the predictive relationship is not stable over time? If it drifts from the beginning to the end of your training data, that would be a bad thing. Then the model you fit is going to have problems. If it drifts a lot, you'll have serious problems. That's what's referred to as concept drift in the machine learning community. And so the objective here is to take a fitted model that you're in the process of fitting to a set of training data. I guess in general, you want to determine whether or not the predictive relationship is stable over the training data. If it is stable, you can view, if it's not stable, you can view that as sort of a check on the model. You probably don't want to use it. You want to understand how it's not stable. Did it abruptly change in the middle of your training data, or did it gradually drift the predictive relationship over the course of your training data? So those type of diagnostics. On the other hand, if you use this approach and conclude that it is stable, then that gives you some confidence in the model and you can go ahead and start using it. And then you might want to implement this in a prospective way, where you're using the predictive model to predict new data as it comes in. Nothing stays the same forever, right? Eventually, if you use the predictive model long enough, as new data comes in, eventually something's going to drift. So to use it prospectively means you're going to monitor as you're using it, the new data, monitor and just try to detect as soon as possible if the predictive relationship changes, because that means it's time to collect a more updated set of data and refit your model. So there's some prior work that has been done on that. I didn't really like any of it. It's all kind of simple and basically just looking at the residuals of the predictive model and doing some type of maybe an exponentially weighted moving average of the model residuals over time. And so what we did, really brief overview, is just looked at the score function. If you're familiar with the Fisher score function, this is a 100-year-old idea. Right? It's just the score function is the derivative. If you look at the log of the likelihood for each observation, when you fit a supervised learning model, you're minimizing let's say the negative log likelihood summed over all the training data, maybe plus a regularization penalty. The Fisher score is the derivative of the log likelihood, and you can do it observation by observation. It's the stochastic gradient and stochastic gradient descent for one observation. Fundamental concept from 100 years old, from right when score function was first introduced. The score function is zero mean if your parameters, if you plug in the theta, let's say theta hat that you estimated from the training data, if you plug that into the model and plug in some new data XY, if that new data follows the same distribution with the same parameters, your score function is zero mean. And score function is a vector, same length as the number of parameters. On the other hand, if for the distribution for X and Y, if it's changed and you got some other new parameters, theta new, that are different from theta, the score vector is no longer zero mean. So basically, to monitor for concept drift, we use this recognition, and we translated the concept drift monitoring problem just into monitoring the mean of the score vector over time. Seeing if the mean of the score vector changes over time. Either retrospectively over your training data, does it change over the course of your training data? Or prospectively over future data, does it change? Which is, I think, kind of a simple idea, but nobody in the concept drift community had noticed that, evidently. And I think it just makes for a, I don't have time to, I think I'm pretty much done here. Time's out. But, we got lots of results. Paper submitted under review at Journal of Machine Learning Research. And it ended up being much, much more powerful and versatile than all of the basically existing methods, which were pretty much just residual-based methods. And it's got some nice diagnostic capabilities too. For if you detect that the mean of your score vector changes, that means you got concept drift. You can look at the mean of the score vector to try to gauge which parameters changed. And actually, you have to actually decouple it by multiplying the score vector by the inverse of the Fisher information matrix, and then it kind of maps the changes back into the original parameters. So it's got, point is, it's got nice diagnostic capabilities too, which probably makes no sense to you because I don't, if I were doing a whole 1 hour talk on this, I'd go into all the details, but I mean, that's just kind of an overview of what the approach is. And I guess I better quit here. 1 minute left for Ajit. You said you had a question you wanted to, or a comment you wanted to say on.
Yeah. Are you finished with your talk?
Yeah. Go ahead.
Oh, okay. So one question I had was that your ALE measure, how does it specialize? Suppose I have parametric model like multiple regression or a logistic regression. Does it simplify?
Yeah, if you have an additive relationship, if your fitted model really is additive in the variables. So a regression model, each of these FJs would just be beta J times XJ. But more generally, if it's additive, then you go through the math, you take the definition, theoretical definition of the AL plot for the Jth predictor, it gives you back the correct function up to a constant, but we don't care about the constant because we zero it anyway. And then it's even more general than that. If your fitted supervised learning model is really second order, so it contains additive in main effects plus up to second order functions, then the second order AL interaction gives you the correct interaction back up to functions of just individual variables. But again, to interpret an interaction doesn't matter if you add in functions of individual variables.
Yeah, I mean, I would have thought that the main effect would correspond to the beta coefficients for those variables, and the interaction would correspond to the interaction coefficients.
Yeah, it does, exactly. And let me just write something on here to clarify that.
And the second question I had was that.
So this one right here would be beta J hat XJ. That's what in a linear regression model.
Yeah.
So the AL plot would just be beta J hat times XJ.
Yeah, that's what I would have thought. Yeah. And the second question I had was that, have you thought of using ALE as a measure for variable selection method?
Oh, well, it gives you variable importance. Yeah, I guess I kind of look at it. Yeah, right. That's a good point. I was kind of thinking before that, you do all the variable selection as you're fitting the model and tuning it. But I think you're right. I think that would be that's hard to do stepwise regression with a neural network, right? I don't know of any good, computationally efficient variable selection methods that you use, they're built right into when you fit a neural network. Like
because R uses AIC criterion for the most part, but that I think is dependent on being able to write down some kind of a likelihood function. And
is that something that's done after the fact, Ajit? After you fit your model, you go back over and look at the variable importances, or is it something done as you're fitting the neural network?
Okay. I'm done.
Okay. Well, yeah, so I think that's a good point. I think that would be one good thing to do. Just fit the model, don't worry about variable selection up front, because that's kind of difficult to do with these complex nonlinear models. And then just look at the AL variable importance measures. And if ones have small importance, you could consider getting rid of them in the model. And then maybe verify whether it was better to get rid of them by following up with cross-validation for the two models with and without them. So yeah, I think that could be a good use of it.
Yeah, might be a good topic for research. Yeah.
Yeah, thanks.
Hey, Dan, if Changhan doesn't have to shut us down immediately here, on the concept drift stuff, which I've found very interesting, how do you detect the drift from zero?
There's something called, if you heard of so basically we've converted concept drift, the problem, into just monitoring for the change in a multivariate vector, the score vector. So basically, detecting changes in the mean of a multivariate vector is an old topic in quality control. What we ended up using was a multivariate exponentially weighted moving average chart.
Mm-hmm.
And then maybe if you want to think of it like this. So if you got two parameters, that means you got S1 and S2, two components of your score vector. Right? If here's how they're sort of distributed when it's normal, they're not everyone's the same. There's some random variation.
Right.
We're trying to detect whether it changes to something else, like over here over time. So, the multivariate exponentially weighted chart, it uses a Hotelling t-squared statistic on the vector.
Okay.
Boils it down to one statistic that just tells you if the mean changes.
Mm-hmm.
If you know, did it change in this direction, or did it change in this direction or this direction? You got to do some follow-up diagnostics.
Right, but it's sort of normal theory based, right? The t-squared is a normal theory, right? Statistic.
Yeah, that's sort of, if you ask a statistician, they'd say yes. If you ask an engineer, they'd say no. And if the exact, you can use Hotelling t-squared distribution, the chi-squared distribution, or F distribution if you estimate the covariance. If you want to analytically determine the control limits, then yes, that's based on normality assumption. I think that's kind of silly in modern day environment where you can empirically estimate, because we got a lot more data now. Just if you empirically estimate the control limits, then you don't have to worry so much about being normal. The statistic itself is just S bar. Well, S bar over some region minus, I'll call it mu S, where mu S would be like an mu hat S estimate over the training data. S bar would be an estimate over some small window of new data. Transpose times your covariance matrix of S inverse times S bar minus mu S.
Mm-hmm. Right.
That's the statistic. To me, this, whether or not it's multivariate normal or not, this statistic still is conceptually meaningful. The more S bar differs from mu S, the larger it is. The only place you need the normality assumption is just to determine the control limits. If you're comfortable saying that this statistic is still conceptually meaningful. I think this is maybe like the likelihood ratio statistic if the data really is multivariate normal.
Right.
Not multivariate normal, it's no longer than the likelihood ratio statistic, but it's still meaningful.
Yeah. I have a situation that is kind of related to this, but the whole issue is detecting in the presence of natural variation in nature that something actually isn't lining up anymore. And that's why I was particularly interested in how you were, you were doing that. If the noise is much smaller compared obviously to the movement, right, then that's fine. But sometime I'll explain my situation to you. It's not exactly this, but this is the neatest thing I've seen to actually think about it. So thanks.
Okay. Yeah, thank you.
Professor, can I also pick your brain as well about concept drift?
Sure. Yeah.
Well, and so I don't know too much about the statistical. I've observed this problem actually in industry, and so it's quite perplexing to me. I think one of the things that bothers me right now with the way that they approach this problem is that it seems like they always have to retrain the model. So do you know of any approaches where the fact that the concept is changing, right? The distribution is changing, is naturally incorporated into the problem?
That would probably be case dependent. Well, what this method does is just, tell you if it's drifting.
Right.
It gives you some diagnostic information to try to help you understand how it's drifting. Here's an old credit risk example where, remember the crash? And, I think can't see the axis here, sorry. Oh, expand it. So this was credit risk monitoring data. This axis is time. Here's when the stock market started to crash in, I think it was like December of 2007. And then just gradually it tanked overall the whole course of 2008.
Mm-hmm.
This axis right here is Barry. This is like the scalar EWMA statistic, multivariate.
Mhm.
So it boils down into one scalar statistic. Here's the control limit determined empirically by applying it to a set of data before we thought there was any drifting.
Mhm.
Mm-hmm.
So then what you do is you monitor that statistic in the future going forward, and you see if it rises above the control limit.
Mm-hmm.
Our statistic down here is the standards residual base, the existing concept drift methods, the residual base statistic. It exceeded the control limit about when the stock market crashed.
Right.
Our method exceeded the control limit, fairly consistently starting back in, was it March of 07? Let's see. Yeah, March of 07, 9 months before the crash.
Mm-hmm.
So it was much more sensitive and it detected that conditions were changing long before it, surfaced in the stock market crashing.
Mm-hmm.
But what it does, it just signals that something.
There's nothing related to retraining or.
Yeah, well, I was going to say I got kind of long-winded there, but then the next step is, there's a follow-up diagnostics. If you take the score vector and multiply that by the inverse Fisher information matrix, it kind of converts it back to the original parameters. So here's a plot of the sort of an EWMA on the original, the individual coefficients.
Mm-hmm.
Here's one of the predictor variables in the model.
Mm-hmm.
X1 was the risk score from in previous model they had. Right? Because they were using a previous model, they thought, well, we already trained the previous model. We want to train a better model. Why not just use the prediction from the previous model as a predictor? And then when we train the new model, if that's important, that'll surface as an important predictor. And if not, it won't. So that was a predictor in the model. And this shows that predictor, it's sort of, you can kind of think of this axis now as like the, sort of a guess of where the actual theta is without having to refit the model, at each time point, just looking at the score function. It kind of tells you how that parameter has changed.
Right.
It says that parameter started to decrease here and then really decreased here. That means the coefficient for the coefficient for the score from the previous model became less relevant.
Mm-hmm. Right, sort of like you're just monitoring the gradient, right? And how the gradient changes, right, also is indicative of how the parameters then ought to be changed in your.
Right. So maybe to get to your question, how would you actually take that into account? If you're constantly drifting and can't control that and it's just there, how you would incorporate that in the model? You'd probably use some of these diagnostics to help you understand what the drift is. And then unfortunately, it'd be up to you. You'd have to sit down and think about how can I modify the model? What terms can I add in the model to kind of incorporate this time varying nature? And I don't think there's any, standard answer to that. It'd just be case dependent and kind of be based on how clever you were.
Because there's also this work, I mean, I don't know if you're very familiar with it, but there is this work in machine learning on online learning, right, where they try to pose this game where you just get new functions sort of at every every iteration. But it's very in my opinion, very pessimistic because there's no actual structure that is imposed between the different functions that you could be obtaining. And so, yeah, I guess I was always curious if there is something that's sort of in between that maybe assumes some kind of probabilistic structure.
Yeah, you're talking about just some model structure that would kind of incorporate the time dependency.
Right.
Yeah, I don't know. I mean, in regression, you could have time varying coefficients. And then what do they call that? They call that DLM, dynamic linear models. In econometrics, you see it. And that's what they have. It's just like a linear regression model, but your betas, the coefficients, are functions of time. So there's probably, but those are all model specific.
I see.
I don't know how you do that in a neural network. It'd be, if you wanted to let every coefficient be a function of time, all of a sudden your dimensionality explodes and would probably not tractable. But there might be, actually looked into it. It's interesting thought. There might be something in the literature on.
Yeah, I haven't seen anything, so I don't
Yeah.
know. And I think
Yeah,
it would
maybe-
affect also how you choose to do the optimization, right? The training of the model as well.
Yeah, you'd probably want to heavily regularize so that your coefficients couldn't jump,
Yeah.
quickly over time.
But in the online learning setting, they always care about, bounds on regret, right? So it's always sort of like in hindsight, if you could do something, right? And comparing how you did at each step versus how you would do it in hindsight.
Okay.
But it's, as far as I can tell, it's more of a theoretical, well, there are some things that have come out of that sort of analysis, but it's more of a theoretical concept, I think, than something practical. And then
That's a problem. That's a problem with 97% of the
literature. Yeah, I guess the last question too is that, so I think one of the implicit assumptions that you have here too is that the derivative is zero, right? That you actually have fit your model, right, and actually obtained a minimizer, right, or stationary.
Yeah, right.
But a lot of times in ML too, because we're applying these stochastic methods to train these models, at least the high dimensional, the large scale neural networks, you're really getting an approximate minimizer, right? So you never really know whether or not your gradient is actually zero.
Yeah, that's an interesting point. I think this would all still work. It's just, we're trying to detect a change in the mean of the score vector.
Right.
It doesn't have to be a change in the mean from zero.
Right.
So
Right.
if you're non-zero mean, you could still use it to detect a change away from that. And I think I'd have to think through it, but I think it'll still work for the same. I didn't mention this, but most time when you fit a machine learning model, you don't just minimize the log likelihood, negative log likelihood.
Right.
Right. You put regularization in. You have to, otherwise you get terrible model that overfits. This is all still fine if you're regularizing it. The score function for just the log likelihood, derivative of just the log likelihood, is not zero if you got a regularization, even if you've optimized it to the minimum. Just the derivative of the log likelihood part isn't zero because you got the regularization term too. Basically, this all still works just fine.
Yeah, and I guess the last thing that's in the back of my mind too is when we use SGD to actually train machine learning systems, a lot of times we are sampling. We're sampling not with replacement, without replacement, right? And sometimes I wonder if part of the reason why that has to do with with this concept drift phenomenon, if there's a way to actually formalize it.
Sampling without replacement, meaning you don't pass over the training data multiple times. You've got so much.
No, so meaning that, so normally they just will shuffle the data, or not even shuffle at all, right? And then when you perform your SGD, you're just taking stochastic gradient steps based off of the order of the data as it has been sort of received, right? So it's actually kind of consistent with sort of an online learning. they analyze this online gradient descent kind of a method.
Okay. What have you, so in online learning, what I've seen, like the multi-arm bandit thing, where you're trying to sort of optimize something, often as a discrete set of choices by,
Yeah, so I'm not talking about the multi-arm bandit setting. I'm talking more about, I guess, the way that people have posed it is really an online optimization. So they just assume that you're being handed a function.
So it's like adaptively as new data comes in, you just kind of
exactly
update your
and
model.
sort of like, rather than, I think you're primarily discussing situation where you're sort of doing everything sort of offline. Maybe at some point you detect and then you choose to retrain, from my understanding of what you're describing.
Right, and then just the way you'd apply this,
adaptively change, right, this model as I go.
Yeah, that's a good point. That's actually kind of considered one type of concept drift, so we're just detecting concept drift. We're not, and there is an online part, but the online part would just be, you've already trained your model offline. You're not updating your model, but online you can still calculate the score vector, even if you're not using it, to change the parameters. You can still calculate the score vector using the old parameters. for every new online observation.
Mhm.
That's our prospective part. So that's the online part. But then I have seen, the one concept drift approach is to online do what you said, to do, adaptively, you're actually trying to change the model as you get new data. I guess the way ours would fit in there is you would use ours to detect online as new data comes in, whether something changed.
Right.
If you didn't detect anything change, then don't waste your time and try to update the model. Just keep the same model. On the other hand, when you do detect that something changed, you'd probably just grab a more recent batch of training data and sort of refit the model to that.
Yeah, and that's what has to happen in practice, partly due to, well, there's multiple reasons for that.
Right. Yeah, online, continuously adaptively changing anything is usually kind of risky.
Yeah, so thank you.
Yeah, thank you. Good questions and comments.
Thank you, Dan, for the great talk and also very interesting discussions.
Yeah, well, thank you for inviting me. I'm glad you did.
Sure. Yeah.
All right. Bye-bye, guys. So talk to you later.